Hello and welcome to Code Skwela. And now we are on our hour number 5. And so just a quick recap on our previous hour of lectures. So if you can still remember, several points have been discussed. One of those is conditions. So part of C is you can do conditional statements in the form of if or if else. uh, yeah, and then you have also discussed different operators. One of those is equality operators, wherein you can use the double bar symbols for or, and then the and or the double ampersands. Another thing also is that has been discussed is the different loops or looping statements, or if you can recall, loops are uh, a way of running code repeatedly. Okay, and so several of those loops has been the while loop, you have the for loop, and then the do while loop. So those are the major looping statements within C. Another thing also is that with loops you can also nest them, or what we commonly call as nested loops. So you can put a for loop within for loops and within for loops, and so on and so forth. And so you can do a different variations of those loops, like putting for loops within while loop or doing for loops within do while loop. So yeah, it depends on your logic. uh, yeah, also he has discussed the floating point imprecision, wherein if you're dealing with numbers, especially with uh, numbers that has fractional parts, then you might be dealing with something precision. So yeah, you could come across different uh, uh, ranges of precisions that you will deal with C. So right, so yeah, and so yeah, uh, we will not be further discussing this to any longer, so that we can continue with our hour number 5. So we have already finished 4 hours of it, and now we're entering the 5th hour, and hopefully we can continue learning more about C. And so yeah, I always have my trusty pen and paper here to take note of uh, the lecture. Let me just, what's the date today? Yeah, 23, March 23. So yeah, we should be starting from where we left off. So join me as we go through another hour of this lecture for the Harvard CS50 Computer Science course. And again, please don't forget to like and subscribe to our channel, so that you can get updated to our future videos, especially new tutorials that would come out in the future. Okay, so yeah, uh, enjoy and let's learn.
Think back last week when we had 3 bits and we counted from like 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. I think I asked the question, how would we count to 8? Someone proposed, well, we need a 4th bit. That's fine if you have a 4th bit, if you have access to another light bulb or transistor. If you don't, though, the next number after this is technically 1000. But if you don't have space for or hardware for that 4th bit, you might as well just be representing the number 0.
We just
So
reset.
in the world of integers, if you're only using 3 bits, those 3 bits eventually overflow when you count past 7, because what should be 8 can't fit, so to speak.
It
So it
exceeded
rolls
its
back over
range.
to 0.
Yeah.
And as arcane as this problem might seem, we humans have done this a couple of times. You might recall knowing about or reading about
Y2K
the
bug.
Y2K problem,
Yeah.
where a lot of people thought the world was going to end. Why? Because on January 1st of 2000, a lot of
999.
computers, presumably, were going to update their clocks from 1999 to the year 2000. The problem is, though, for decades, for efficiency, we humans were honestly in the habit of not storing years as 4 digits. Why? Because that's just a lot of space to waste, especially since like centuries don't happen that often. So a lot of computer systems, especially early on, when hardware was very expensive and memory was very tight, just stored the last 2 digits of any year. Problem, of course, on January 1st of 2000 is that 99 rolls over to 100, but if you don't have room for another digit, it's just 00. And if your code assumes a prefix of 19, Well, we just went from the year 1999 back to the year 1900. Thankfully, long story short, a lot of people wrote a lot of code in a lot of old languages and mostly warded off this problem, so the world did not end. The next time the world might end, though, is on January 19th, 2038. Now, that might feel like a long time away, but so did the year 2000 at one point. Why might clocks again break in today's modern computers in 2038, might you think?
What do you think? That's quite
Indeed. So this refers to some number of seconds. So it turns out that the way computers generally keep track of time is they count the total number of seconds since the epoch, which is defined as January 1st, 1970.
70.
Why? It was just a good year to sort of start counting at when computers really came onto the scene. Unfortunately, most computers use 32 bits to count the number of seconds since January 1st, 1970, the implication of which is we can only count up to roughly 2 billion seconds. 2 billion seconds is going to happen in 2038, at which point 31 ones are going to roll over as follows. That number 2 billion, which is the max, because if you're representing positive and negative numbers, recall that you can only count as high as positive 2 billion or negative 2 billion, looks like this. This is roughly the number 2 billion in binary. It's all ones with 1 0 way over here. If I count 1 second past that 2 billion number, give or take, that means like, all right, I add 1, I carry the 1. It's just like nines becoming zeros in decimal. If I keep this sort of simple animation, and I keep carrying the 1, carrying the 1, carrying the 1, 1 second after 2 billion seconds, give or take, I have this number in the computer's memory. So there's still one bit that's a 1 all the way to the left. Unfortunately, that bit often represents negativity. Whereby if that first bit is negative, that represents that the rest of this somehow represents a negative number. It's not negative 0. There's a fancier representation. But a very big positive number very suddenly becomes a very big negative number. And that number is roughly negative 2 billion. That means computers in 2038 on that date are going to accidentally think that it's been negative 2 billion seconds since January 1st, 1970, which is going to make computers potentially think it's 1901. So what is the solution to the 2038 problem, perhaps? Y2K was because we were using 2 digits for years. What about 2038? More bits. And thankfully, we're getting a little better at lessons learned here. And computers now are increasingly using 64 bits. And all of us will be long gone by the time we run out of that number of seconds. So it's someone else's problem many, many years from now.
Continuous
but
updates.
That's really the fundamental solution. If you're running up against something finite, well, just kick the can further and just give yourself more bits. And frankly, because hardware is so much cheaper these days, computers are so much faster, it's not as big of a deal as it might have been decades ago. But that's indeed the solution. But this arises in very common contexts. In fact, let me go ahead and write a real quick program here called pennies. Right? You might think that just converting dollars to pennies in US currency might be simple. But let me go ahead and do this. In pennies.c, I'm going to go ahead and include cs50.h. And I'm going to include standard.io.h, int main void as my starting point. And now down here, I'm going to do this. I'm going to get a float called amount. I'm going to ask the user for some amount of dollars, so a dollar amount. And I'm going to store that in a variable called amount. Then I'm going to simply convert that amount to pennies by doing, say, how about amount times 100. And then I'm going to go ahead and print out that the number of pennies is %i, because that's just an integer in pennies, \n, quote unquote, comma, pennies. All right, so if I didn't make any mistakes here, let me make pennies, /pennies, and suppose I have, say, 99 cents, so 0.99, that's 99 pennies. Suppose I have $1.23. That's pretty good. Suppose I have $4.20. There's that imprecision issue, and this isn't even that big of an amount. Now, not a big deal if, like, the cashier gives you 1 penny less than you're owed, but you can imagine this adding up. You can imagine this being worrisome for financial implications, for financial transactions, for scientific measurements and the like. My program can't even handle this. Well, there are some solutions here. And it looks like what's really happening, if I print it out using the %f with a 0.50 or whatever to see more decimal points, presumably the computer is struggling to represent $4.20 precisely. It's probably storing $4.19.9999 something cents. So it's close, but it's not quite there. So I could at least solve this by rounding up, for instance. And it turns out there is a round function out there. And it turns out that it's in a library called the math library. And you would know this by looking at online documentation and the like, as we'll point you to. And if I now make pennies again and do /pennies, I can now do $4.20. And voila, now it's correct. So at least in this context, it seems like a solvable problem. But it's certainly something I need to be mindful of nonetheless. Unfortunately, even professional, full-time programmers over the years have not been particularly attentive to these kinds of details. And in a class like this, the goal is not just to teach you programming, but to really teach you what's going on underneath the hood, so to speak, so that you have a bottom-up understanding of how data is represented, how computers are manipulating it, so that you are not on the failing end of some program having some bug, and so that we as a society are not beholden to those kinds of mistakes too. And this happens, unfortunately, all of the time. This is a Boeing airplane that a few years ago needed to be rebooted after every 248 days. Why? Because this Boeing airplane software was using a 32-bit integer, counting up tenths of a second to keep track of something or other related to its electrical power. And unfortunately, after 248 days of the airplane being continuously on, which in the airline industry is apparently not uncommon to make every dollar count, keeping the planes up and running all the time, the 32-bit number would roll over, and the power would shut off on the airplane as a side effect because of sort of undefined behavior in that case. The temporary solution by Boeing at the time was apparently essentially sort of operating system style, well, have you rebooted your plane? And that was indeed the fix until they rolled out an actual software patch. This stuff really matters. And the more hardware we carry around and the more we as a society use these kinds of devices, the more of these problems we're going to run into down the road. That's it for CS50. We'll see you next time.
Oh, it's over? Huh. Okay. What are we now going to do? Arrays. Okay. Arrays. Yeah. This is quite a topic also.
This is CS50, and this is week 2. Now that you have some programming experience under your belt in this more arcane language called C, among our goals today is to help you understand exactly what you have been doing these past several days, wrestling with your first programs in C, so that you have more of a bottom-up understanding of what some of these commands do, and ultimately what more we can do with this language. So this, recall, was the very first program you wrote, I wrote in this language called C, much more textual, certainly, than the Scratch equivalent. But at the end of the day, computers, your Mac, your PC, VS Code doesn't understand this actual code. What's the format into which we need to get any program that we write? Just to recap. So binary, otherwise known as machine code, language, right? The zeros and ones that your computer actually does understand. So somehow we need to get to this format. And up until now, we've been using this command called make, which is sort of aptly named because it lets you make programs. And the invocation of that has been pretty simple. Make hello sort of looks in your current directory or folder for a file called hello.c implicitly. And then it compiles that into a file called hello, which itself is executable, which just means runnable, so that you can then do /hello. But it turns out that make is actually not a compiler itself. It does help you make programs, but make is this sort of utility that comes on a lot of systems that makes it easier to actually compile code by using an actual compiler the program that converts source code to machine code on your own Mac or PC or whatever cloud environment you might be using. In fact, what make is doing for us is actually running a command automatically known as clang for C language. And so in fact, here, for instance, in VS Code is that very first program again, this time in the context of a text editor. And I could compile this with make hello, but let me go ahead and use the compiler itself manually. And we'll see in a moment why we've been automating the process with make. I'm going to run clang instead, and then I'm going to run hello.c. So it's a little different how the compiler's used. It needs to know explicitly what the file is called. I'll go ahead and run clang hello.c, enter. Nothing seems to happen, which generally speaking is a good thing, because no errors have popped up. And if I do ls now for list, you'll see there is not a file called hello, but there is a curiously named file called a.out. This is a historical convention, stands for assembler output. And this is just the default file name for a program that you might compile yourself manually using clang itself. Let me go ahead now, though, and point out that that's kind of a stupid name for a program, even though it works. /a.out would work. But if you actually want to customize the name of your program, we could just resort to make, or we could do explicitly what make is doing for us. Because it turns out some programs, among them make, support what are called command line arguments. And more on those later today. But these are like literally words or numbers that you type at your prompt after the name of a program that just influences its behavior in some way. It modifies its behavior. And it turns out, if you read the documentation for clang, you can actually pass a -o for output command line argument that lets you specify explicitly what do you want your outputted program to be called. And then you go ahead and type the name of the file that you actually want to compile from source code to machine code. Let me go ahead and hit enter now. Again, nothing seems to happen. And I type ls, and voila. Now we still have the old a.out because I didn't delete it yet. And I do have hello now. So /hello, voila, runs hello world again. And let me go ahead and remove this file. I could, of course, resort to using the Explorer on the left-hand side, which I am in the habit of closing just to give us more room to see. But I could go ahead and right-click or control-click on a.out if I want to get rid of it. Or again, let me focus on the command line interface. And I can use, anyone recall? We didn't really use it much, but
rm.
What command removes a file?
rm.
rm. So rm for remove, rm, a.out, enter, remove regular file, a.out, y for yes, enter. And now if I do ls again, voila, it's gone. All right, so let's now enhance this program to do the second version we ever did, which was to also include CS50.h so that we have access to functions like getString and the like. And let me go ahead and do string name gets, getString, what's your name, question mark. And now let me go ahead and say hello to that name with our %s placeholder, comma name. So this was version 2 of our program last time that very easily compiled with make hello. But notice the difference now. If I want to compile this thing myself with clang using that same lesson learned, all right, let's do it. Clang -o hello, just so I get a better name for the program, hello.c. Enter. And a new error pops up that some of you might have encountered on your own. So it's a bit arcane here, and there's this mention of a cryptic looking path with temp for temporary there. But somehow my issue's in main, as we can see here. It somehow relates to hello.c, even though we might not have seen this language last time in class. But there's an undefined reference to getString, as though getString doesn't exist. Now, your first instinct might be, well, maybe I forgot CS50.h, but of course I didn't. That's the very first line of my program. But it turns out make is doing something else for us all this time. Just putting CS50.h or any header file at the top of your code, for that matter, just teaches the compiler that a function will exist. It sort of asks the compiler to trust that I will eventually get around to implementing functions like getString in CS50.h and standard.io.h like printf therein. But this error here, some kind of linker command, relates to the fact that there's a separate process for actually finding the zeros and ones that CS50 compiled long ago for you, that the authors of this operating system compiled for you long ago in the form of printf. We need to somehow tell the compiler that we need to link in code that someone else wrote, the actual machine code that someone else wrote and then compiled. So to do that, you'd have to type -l CS50, for instance, at the end of the command. So additionally telling clang that not only do you want to output a file called hello and you want to compile a file called hello.c, you also want to, quote unquote, link in a bunch of zeros and ones that collectively implement getString, and printf. So now if I hit enter, this time it compiled OK. And now if I run /hello, it works as it did last week, just like that. But honestly, this is just going to get really tedious really quickly. Notice already, just to compile my code, I have to run clang-o hello hello.c -lcs50. And you're going to have to type more things too. If you wanted to use the math library, like to use that round function, you would also have to do -lm typically to specify give me the math bits that someone else compiled. And the commands just get longer and longer. So moving forward, we won't have to resort to running Clang itself. But Clang is indeed the compiler. That is the program that converts from source code to machine code. But we'll continue to use make because it just automates that process. And the commands are only going to get more cryptic the more sophisticated and more featureful your programs get. And make, again, is just a tool that makes all that happen, so to speak. Let me pause there to see if there's any questions before then we take a look further under the hood. Yeah, in front. Sure, and let me come back to that in a moment. What does the -lcs50 mean? We'll come back to that visually in just a moment. But it means to link in the zeros and ones that collectively implement getString and printf. But we'll see that visually in a sec. Yeah, behind you. Really good question. How come I didn't have to link in standard I/O? Because I used printf in version 1. Standard I/O is just literally so standard that it's built in. It just works for free. CS50, of course, is not. It did not come with the language C or the compiler. We ourselves wrote it. And other libraries, even though they might come with the language C, they might not be enabled by default, generally for efficiency purposes. So you're not loading more zeros and ones into the computer's memory than you need to. So standard I/O is special, if you will. Other questions? Yeah. Oh, what does the -o mean? So -o is shorthand for the English word output. And so -o is telling Clang to please output a file called hello, because the next thing I wrote after the command line, recall, was clang -o hello, then the name of the file, then -lcs50. And this is where these commands do get and stay fairly arcane. It's just through muscle memory and practice that you'll start to remember, oh, what are the other commands that what are the command line arguments you can provide to programs? But we've seen this before. Technically, when you run make hello, the program is called make. Hello is the command line argument. It's an input to the make function, albeit typed at the prompt, that tells make what you want to make. Even when I used rm a moment ago and did rm of a.out, the command line argument there was called a.out, and it's just telling rm what to delete. It is entirely dependent on the programs to decide what their conventions are, whether you use -this or -that. But we'll see over time which ones actually matter in practice. So to come back to the first question about what actually is happening there, let's consider the code more closely up. So here is that first version of the code again with standard io.h and only printf, so no CS50 stuff yet, until we add it back in and had the second version where we actually get the human's name. When you run this command then, there's actually a few things that are happening underneath the hood. And we won't dwell on these kinds of details. Indeed, we'll abstract it away, so to speak, by using make. But it's worth understanding, at least from the get-go, how much automation is going on so that when you run these commands, it's not magic. You actually do have this bottom-up understanding of what's going on. So when we say you've been compiling your code with make, that's a bit of an oversimplification. Technically, every time you compile your code, you're having the computer actually do 4 distinct things for you. And this is not 4 distinct things that you need to sort of memorize and remember every time you run your program what's happening. But it helps to sort of break it down into building blocks as to how we're getting from source code, like C, into zeros and ones. It turns out that when you compile, quote unquote, your code, technically speaking, you're doing 4 things sort of automatically and all at once. Pre-processing it, compiling it, assembling it, and linking it. Just humans decided, let's just call the whole process compiling. But for a moment, let's just consider what these steps are. So pre-processing refers to this. If we look at our source code here, version 2, that uses the CS50 library and therefore getString, notice that we indeed have these include lines at top. And they're kind of special versus all the other code we've written because they start with hash symbols specifically. And that's sort of a special syntax that means that these are technically called preprocessor directives. A fancy way of saying they're handled special versus the rest of your code. In fact, if we focus on CS50.h, recall from last week that I provided a hint as to what's actually in CS50.h, among other things. Like, what was the one salient thing that I said was in CS50.h, and therefore why we were including it in the first place?
The functions for the
So getString, specifically the prototype for getString. We haven't made many of our own functions yet, but recall that anytime we've made our own functions and we've written them like below main in a file, we've also had to somewhat stupidly copy paste the prototype of the function at the top of the file just to teach the compiler that this function doesn't exist yet. It does down there, but it will exist. Just trust me. So again, that's what these prototypes are doing for us. So therefore, in my code, if I want to use a function like getString, or printf for that matter, they're not implemented clearly in the same file. They're implemented elsewhere. So I need to tell the compiler to trust me that they're implemented somewhere else. And so technically, inside of CS50.h, which is installed somewhere in the cloud's hard drive, so to speak, that you all are accessing via VS Code, there's a line that looks like this. A prototype for the getString function that says the name of the function's getString. It takes one input or argument called prompt. And that type of that prompt is a string. GetString, not surprisingly, has a return value, and it returns a string. So literally, that line and a bunch of others are in CS50.h. And so rather than you all having to copy paste the prototype, you can just trust that CS50 figured out what it is. You can include CS50.h, and the compiler is going to go find that prototype for you. Same thing in standard IO. Someone else. What must clearly be in standard IO.h, among other stuff, that motivates our including standard IO.h too? Yeah. Printf, the prototype for printf. And indeed, I'll just change it here in yellow to be the same. And it turns out the format, the prototype for printf is actually pretty fancy because, as you might have noticed, printf can take one argument, just something to print, two, if you want to plug a value into it, three or more. So the ... just represents exactly that. It's not quite as simple a prototype as getString, but more on that another time. So what does it mean to pre-process your code? The very first thing the compiler, Clang in this case, is doing for you when it reads your code top to bottom, left to right, is it notices, ooh, here is hash include. Oh, here's another hash include. And it essentially finds those files on the hard drive, CS50.h, standard IO.h, and does the equivalent of copying and pasting them automatically into your code at the very top, thereby teaching the compiler that getString and printf will eventually exist somewhere. So that's the pre-processing step, whereby, again, it's just doing a find and replace of anything that starts with hash include. It's plugging in the files there so that you essentially get all the prototypes you need automatically. OK, what does it mean then to compile the result? Because at this point in the story, your code now looks like this in the computer's memory. It doesn't change your file. It's doing all of this in the computer's memory or RAM for you. But it essentially looks like this. Well, the next step is what's technically really compiling, even though, again, we use compile as an umbrella term. Compiling code in C means to take code that now looks like this in the computer's memory and turn it into something that looks like this, which is way more cryptic. But it was just a few decades ago that if you were taking a class like CS50 in its earlier form, we wouldn't be using C if it didn't exist yet. We would actually be using this, something called assembly language. And there's different types of or flavors of assembly language. But this is about as low level as you can get to what a computer really understands, be it a Mac or a PC or a phone, before you start getting into actual zeros and ones. And most of this is cryptic. I couldn't really tell you what this is doing unless I really thought it through carefully and rewound mentally years ago from having studied it. But let's highlight a few key words in yellow. Notice that this assembly language that the computer is outputting for you automatically still has mention of main, and it has mention of getString, and it has mention of printf. So there's some relationship to the C code we saw a moment ago. And then if I highlight these other things, these are what are called computer instructions. At the end of the day, your Mac, your PC, your phone actually only understands very basic instructions like addition, subtraction, division, multiplication, move into memory, load from memory, print something to the screen, like very basic operations. And that's what you're seeing here. Yeah. These assembly instructions are what the computer actually feeds into the brains of the computer, the CPU, the central processing unit. And it's that Intel CPU or whatever you have that understands this instruction and this one and this one and this one. And collectively, long story short, all they do is print hello world on the screen, but in a way that the machine understands how to do. So let me pause here. Are there any questions on what we mean by pre-processing, which just finds and replaces the hash includes symbols, among others, and compiling, which technically takes your source code once pre-processed and converts it to that stuff called assembly language? Correct. Each type of CPU has its own instruction set. Indeed. And as a teaser, this is why, at least back in the day when we used to like install software from CD-ROMs or some other type of media, this is why you can't take a program that was sold for a Windows computer and run it on a Mac or vice versa, because the commands, the instructions that those two products understand are actually different. Now, Microsoft or any company could generally write code in one language like C or another, and they can compile it twice, saving a PC version and saving a Mac version. It's twice as much work, and sometimes you get into some incompatibilities. But that's why these steps are somewhat distinct. You can now use the same code and support even different platforms or systems if you'd want. All right, assembling. Thankfully, this part is fairly straightforward, at least in concept, to assemble code, which is step 3 of 4, that is just happening literally for you every time you run make or in turn clang. This assembly language, which the computer generated automatically for you from your source code, is turned into zeros and ones. So that's the step that last week I simplified and said, when you compile your code, you convert it to source code, from source code to machine code. Technically, that happens when you assemble your code. But no one in normal conversations says that. They just say compile for all of these terms. All right, so that's assembling. There's one final step. Even in this simple program of getting the user's name and then plugging it into printf, I'm using 3 different people's code, if you will. My own, which is in hello.c, some of CS50's, which is apparently in hello.c, which is in CS50.c, which is not a file I've mentioned yet, but it stands to reason that if there's a CS50.h that has prototypes, turns out the actual implementation of getString and other things are in CS50.c. And there's a third file somewhere on the hard drive, so to speak, that's involved in compiling even this simple program. Hello.c, CS50.c, and by that logic, what might the other be? Yeah. Standard.io.c. And that's a bit of a white lie, because that's such a big, fancy library that there's actually multiple files that compose it. But the same idea, and we'll take the simplification. So when I have this code now, and I compile my code here, I get those zeros and ones that end up taking hello.c and turning it effectively into zeros and ones that are combined with CS50.c, followed by standard.io.c as well. So let me rewind here. Here might be the zeros and ones for my code, the 2 lines of code essentially that I wrote. Here might be the zeros and ones for what CS50 wrote some years ago in CS50.c. Here might be the zeros and ones that someone wrote for standard.io decades ago. The last and final step is that linking command that links all of these zeros and ones together, essentially stitches them together into one single file called hello, or called a.out, whatever you name it. That last step is what combines all of these different programmers' zeros and ones. And my God, like now we're really in the weeds. Who wants to even think about running code at this level? You shouldn't need to, but it's not magic. When you're running make, there's just some very concrete steps that are happening that humans have developed over the years, over the decades, that sort of break down this big problem of source code going to zeros and ones, or machine code, into these very specific steps. But henceforth, you can call all of this compiling. Questions or confusion? Yeah? Sure. What does a.out signify? A.out is just the conventional default file name for any program that you compile directly with a compiler like Clang. It's just kind of a meaningless name, though. It stands for assembler output. And assembler might now sound familiar from this assembling process. It's just kind of a lame name for a computer program. And so we can override it by outputting something like hello instead. Yeah? So there are, to recap, there are other prototypes in those files, CS50.h, standard.io.h. Technically, they're all included atop your file, even though you, strictly speaking, don't need most of them. But indeed, they are there, just in case you might want them. And finally, any other questions? Yeah? Does it matter what order we're telling the computer to run? Sometimes with libraries, yes, it matters what order they are linked in together. But for our purposes, it's really not going to matter. It's just going to make is going to take care of automating that process for us. All right, so with that said, henceforth, compiling technically is these 4 things, but we'll focus on it just as a higher level concept, an abstraction, if you will, known as compiling itself. So another process that we'll now begin to focus on all the more this week, because invariably this past week you ran up against some challenges. You probably created your very first bugs or mistakes in a program. And so let's focus for a moment on actual techniques for debugging. As you spend more time this semester, in the years to come, if you continue to program, you're never, frankly, probably going to write bug-free code. Ultimately, your programs are just going to get more featureful, more sophisticated, and we're all just going to start to make more sophisticated mistakes. And to this day, I write buggy code all the time, and I'm always horrified when I do it up here, but hopefully that won't happen too often. But when it does, it's just a process now of debugging, trying to find the mistakes in your program. And you don't have to just stare at your code or sort of shake your fist at your code. There are actual tools that real-world programmers use to help debug their code and find these faults. So what are some of the techniques and tools that folks use? Well, as an aside, if you've ever bug in a program is a mistake. That's actually been around for some time. If you've ever heard this tale, some 50 plus years ago in 1947, this is actually an entry in a logbook written by a famous computer scientist named Grace Hopper, who happened to be the one to record the very first discovery of a quote unquote actual bug in a computer. This is actually like a moth that had flown into, at the time, it was a very sophisticated system known as the Harvard Mark II computer, sort of very large, sort of refrigerator-sized type systems in which an actual bug caused an issue. The etymology of bug, though, actually predates this particular instance. But here you have, as any computer scientist might know, the example of the first physical bug in a computer. How, though, do you go about removing such a thing? Well, let's consider a very simple scenario from last time, for instance, when we were trying to print out various aspects of Mario, like this column of 3 bricks. Let's consider how I might go about implementing a program like this. And let me switch back over to VS Code here. And I'm going to go ahead and write a program. And I'm not going to trust myself, so I'm going to call it buggy.c from the get-go, knowing that I'm going to mess something up. But I'm going to go ahead and include standardIO.h. And I'm going to go ahead and define main as usual. So hopefully no mistakes just yet. And now I want to print those 3 bricks on the screen using just hashes for bricks. So how about for int I gets 0, I less than or equal to 3, I plus plus. Now inside of my curly braces, I'm going to go ahead and print out a hash followed by a \n, semicolon. All right, saving the file, doing make buggy, enter, it compiles. So there's no syntactical errors, like my code is syntactically correct, but some of you have probably seen the logical error already, because when I run this program, I don't get this picture, which was 3 bricks high. I seem to have 4 bricks instead. Now, this might be jumping out at you why it's happening, but I've kept the program simple just so that we don't have to actually find an actual bug. We can use a tool to find one that we already know about in this case. What might be the first strategy for actually finding a bug like this, rather than just staring at your code, asking a question, trying to sort of just think through the problem? Well, let's actually try to diagnose the problem more proactively. And the simplest way to do this now and years from now is honestly going to be to use a function like printf. Printf is a wonderfully useful function, not for printing formatted strings and all that, for just looking inside the values of variables that you might be curious about to see what's going on. So you know what? Let me do this. I see that there's 4 coming out, but I intended 3. So clearly something's wrong with my I variables. So let me just be a little more pedantic. Let me go inside of this loop and just temporarily say something explicit like I is %i \n, and then just plug in the value of I. Right? This is not the program I want to write. It's the program I'm temporarily writing, because now I'm going to go ahead and say make buggy /buggy. And if I look now at the output, I have some helpful diagnostic information. I is 0, and I get a hash. I is 1, and I get a hash. 2, and I get a hash. 3, and I get a hash. OK, wait a minute. I'm clearly going too many steps, because maybe I forgot that computers are essentially counting from 0. And now, oh, it's less than or equal to. Now you see it. Right? Again, trivial example. But just by using printf, you can see inside of the computer's memory by just printing stuff out like this. And now once you've figured it out, oh, So this should probably be less than 3. Or I should start counting from 1. There's any number of ways I could fix this. But the most conventional is probably just to say less than 3. Now I can go ahead and delete my temporary print statement, rerun make buggy, /buggy, and voila, problem solved. All right, and to this day, I do this, like whether it's making a command line application or a web application or a mobile application, it's very common to use printf or some equivalent in any language just to poke around and see what's inside the computer's memory. Thankfully, there's more sophisticated tools than this. Let me go ahead and reintroduce the bug here. And let me go ahead and reopen my sidebar at left here. And let me go ahead now and recompile the code to make sure it's current. And I'm going to run a command called debug50, which is a command that's representative of a type of program known as a debugger. And this debugger is actually built into VS Code. And all debug50 is doing for us is just automating the process of starting VS Code's built-in debugger. So this isn't even a CS50 specific tool. We've just given you a debug50 command to make it easier to start it up from the get-go. And the way you run this debugger is you say debug50 space, and then the name of the program that you want to debug. So in this case, /buggy. So you don't mention your C file. You mention your already compiled code. And what this debugger is going to let me do is most powerfully walk through my code step by step. Because every program we've written thus far just kind of runs from start to finish, even if I'm not done sort of thinking through each step at a time. With the debugger, I can actually like click on a line number and say pause execution here. And the debugger will let me walk through my code one step at a time, 1 second at a time, 1 minute at a time at my own human pace, which is super compelling when the programs get more complicated and they might otherwise just fly by on the screen. So I'm going to click to the left of line 5 and notice that these little red dots appear. And if I click on one, it stays and gets even redder. And I'm going to now run debug50 on /buggy. And in just a moment, you'll see that a new panel opens on the left-hand side. It's doing some configuration of the screen. And now let me go ahead and zoom out just a little bit here so we can see more on the screen at once. And sometimes you'll see in VS Code that debug console opens up, which looks very cryptic. Just go back to terminal window if that happens, because at the terminal window is where you can still interact with your code. And let's now take a look at what's going on. If I zoom in on my buggy.c code here, you'll notice that we have the same program as before, but highlighted in yellow is line 5. Not a coincidence. That's the line I set a so-called breakpoint at. The little sort of red dot means break here, pause execution here, and the yellow line has not yet been executed. But if I now, at the top of my screen, notice these little arrows. There's one for play. There's one for this, which if I hover over it, says step over. There's another that's going to say step into. There's a third that says step out. I'm just going to use the first of these, step over. And I'm going to do this. And you'll see that the yellow highlight moved from line 5 to line 7 because now it's ready, but hasn't yet printed out that hash. But the most powerful thing here, notice, is at top left here. It's a little cryptic because there's a bunch of things going on that'll make more sense over time. But at the top, there's a section called variables. Below that, something called locals, which means local to my current function, main. And notice, there's my variable called I, and its current value is 0. So now, once I click step over again, watch what happens. We go from line 7 back to line 5. But look in the terminal window, one of the hashes has printed. But now it's kind of printed at my own pace. I can sort of think through this step by step. Notice that I has not changed yet. It's still 0 because the yellow highlighted line hasn't yet executed. But the moment I click step over, it's going to execute line 5. Now notice at top left, I has become 1. And nothing has printed yet because now highlighted is line 7. And so if I click step over again, we'll see the hash. And if I repeat this process at my own human comfortable pace, I can see my variables changing. I can see output changing on the screen. And I can just think about, should that have just happened? And I can pause and give thought to what's actually going on without trying to race the computer and figure it all out at once. I'm going to go ahead and just stop here because we already know what this particular problem is. And that just brings me back to my default terminal window. But this debugger, let me disable the breakpoint now so it doesn't keep breaking. This debugger will be your friend moving forward in order to step through your code, step by step at your own pace, to figure out where something has gone wrong. Printf is great, but it gets annoying if you have to constantly add print this, print this,
Yeah.
print this, print this, recompile, rerun it. Oh, wait a minute, print this, like the debugger just
Yeah. Once you start uh, coding on a daily basis, debugging is quite a time-consuming task. So writing code is one, debugging is another problem also. Since if if unless you are a very very good coder that you have very very minimal bugs in your code, then I think that's great. But the moment you uh, encounter bugs, then stepping through each of the lines, pausing and going through the different uh, variables, so allows you to inspect the contents of whatever data that you are dealing with. It's very uh, helpful as a coder to have that kind of tool. Uh, Whether you're dealing with C, for me, I've been working with C Sharp and using Visual Studio. Visual Studio provides a good set of debugging tools that would allow you to uh, debug or inspect the different parts of your code using the ways of the same way as on C, that is adding breakpoints, and then yeah, inspecting, and you can also inspect the contents of the different data or the variables that you're working. It could be as deep as uh, within your sub functions. Yeah, but yeah, that's one thing that you could expect when you are working with code on a daily basis.
lets you do the equivalent, but automatically. Questions on then this debugger, which you'll see all the more hands-on over time. Questions on debugger? Yeah.
You were using like the step over feature. What do the other features in the debugger do?
Really good question. We'll see this before long, but those other buttons that I glossed over, like step into and step out of, actually let you step into specific functions if I had any more than main. So if main called a function called something, and something called a function called something else, instead of just stepping over the entire execution of that function, I could step into it and walk through its lines of code one by one. So anytime you have a problem set you're working on that has multiple functions, you can set a breakpoint in main if you want, or you can set it inside of one of your additional functions to focus your attention only on that. And we'll see examples of that over time. All right, so what else? And what's the the sort of elephant in the room, so to speak, is actually a duck in this case. Why is there this duck and all of these ducks here? Well, it turns out a third genuinely recommended debugging technique is talking through problems, talking through code with someone else. Now, in the absence of having a family member or a friend or a roommate who actually wants to hear you talk about code of all things, generally programmers turn to a rubber duck or other inanimate objects if something animate is not available. And the idea behind rubber duck debugging, so to speak, is that simply by looking at your code and talking it through, OK, on line 3, I'm starting a for loop, and I'm initializing I to 0. OK, then I'm printing out a hash. Just by talking through your code step by step, invariably finds you having the proverbial light bulb go off over your head because you realize, wait a minute, I just said something stupid, or I just said something wrong. And this is really just a proxy for any other human, teaching fellow, teacher, friend, colleague. But in the absence of any of those people in the room, you're welcome to take on your way out today one of these little rubber ducks and consider using it for real anytime you just want to talk through one of your problems.
So yeah, he was talking about rubber duck. It's a kind of technique that most programmers use, or I don't know if it's actually a technique, but eventually, when you deal with code, especially when you're getting in a kind of trying to think over the logic, you might see developers like staring at the ceiling, or staring at something looking far away. That means that they're getting into that mode of thinking over through the code that you have created or done. I usually do go through that uh, same experience, yeah, while coding. sometimes I just stare at something and then look at the window and then, yeah, going through the logic of the code that I'm doing. There's probably something in it that I could do better or improve better, or if I'm fixing something that, yeah, yeah, it's it's a common occurrence for most developers. So yeah, eventually if you go through that kind of uh, profession of professionally coding, then yeah, you will be experiencing that uh, in your career.
CS50 or maybe life more generally, but having it there on your desk is just a way to help you hear illogic in what you think might otherwise be logical code. So printf, debugging, rubber duck debugging are just 3 of the ways you'll see over time to sort of get to the source of code that you will write that has mistakes, which is going to happen, but it'll empower you all the more to solve those mistakes. Are any questions on debugging in general or these 3 techniques? Yeah. What's the difference between step over and step into? At the moment, the only one that's applicable to the code I just wrote is step over, because it means step over each line of code. If, though, I had other functions that I had written in this program, maybe lower down in the file, I could step into those function calls and walk through them one at a time. So we'll come back to this with an actual example, but step into will allow me to do exactly that. In fact, this is a perfect segue to doing a little something like this. Let me go ahead and open up maybe another file here. Actually, we'll use the same, buggy, and we're just going to write one other thing that's buggy as well. Let me go ahead up here and include, as before, CS50.h. Let me include standard.io.h. Let me do int main void. So all of this, I think, is correct so far. And let's do this. Let's give myself an int called I, and let's ask the user for a negative integer. This is not a function that exists technically yet, but I'm going to assume for the sake of discussion that it does. And then I'm just going to go ahead and print out with %i and a new line whatever the human typed in. So at this point in the story, my program, I think, is correct, except for the fact that getNegativeInt is not a function in the CS50 library or anywhere else. I'm going to need to invent it myself. So suppose in this case that I declare a function called getNegativeInt. Its return type, so to speak, should be int, because as its name suggests, I want to hand the user back an integer. And it's going to take no input to keep it simple. So I'm just going to say void there. No inputs, no special prompts, nothing like that. Let me now give myself some curly braces. And let me do something familiar perhaps now from problem set 1. Let me give myself a variable like n. And let me do the following within this block of code. Assign n the value of getInt, asking the user for a negative integer using getInt's own prompt. And I want to do this while n is less than 0, because I want to get a negative int from the user. And recall, from having used this block in the past, I can now return n as the very last step to hand back whatever the user has typed in, so long as they cooperated and gave me an actual negative integer. Now, I've deliberately made a mistake here. And it's a subtle, sort of silly mathematical one. But let me compile this program after copying now the prototype up to the top, just so I don't make that mistake again. Let me do make buggy, enter. And now let me do /buggy. I'll give it a negative integer like -50. That did not take. How about -5? Maybe it's 2. No. How about 0? All right, so it's clearly sort of working backwards or incorrectly here logically. So how could I go about debugging this? Well, I could do what I've done before. I could use my printf technique and say something explicit like n is %i, new line, comma n, just to print it out. Let me recompile buggy. Let me rerun buggy. Let me type in -50. OK, n is -50. So that didn't really help me at this point, because that's the same as before. So let me do this. Debug 50 /buggy. Oh, but I've made a mistake. So I didn't set my breakpoint yet. So let me go ahead and do this. And I'll set a breakpoint this time. I could set it here on line 8. Let's do it in main as before. Let me rerun debug 50 now on /buggy. That fancy user interface is going to pop up. It's going to highlight the line that I set the breakpoint on. Notice that on the left-hand side of the screen, I is defaulting at the moment to 0 because I haven't typed anything in yet. But let me go ahead now and step over this line that's highlighted in yellow. And you'll see that I'm being prompted. So let's type in my -50, enter. All right, and notice now that I'm stuck in that function. So, all right. So clearly the issue seems to be in my getNegativeInt function. So, OK, let me go ahead and stop this execution. My problem doesn't seem to be in main per se. Maybe it's down here. So that's fine. Let me set my same breakpoint at line 8. Let me rerun debug 50 one more time. But this time, instead of just stepping over that line, let's step into it. So notice line 8 is again highlighted in yellow. In the past, I've been clicking step over. Let's click step into now. And when I click step into, boom, now the debugger jumps into that specific function. And now I can step through these lines of code again and again. I can see what the value of n is as I'm typing it in. I can think through my logic. And voila, hopefully once I've solved the issue, I can exit the debugger, fix my code, and move on. So step over just goes over the line but executes it. Step into lets you go into other functions you've written. So, all right, so let's go ahead and do this. We've got a bunch of possible approaches that we can take to solving some problem. Let's go ahead and pace ourselves today, though. Let's take a 5-minute break here. And when we come back, we'll actually take a look at that computer's memory we've been talking about. See you in 5. All right. So let's dive back in. And up until now, both by way of week 1 and problem set 1, for the most part, we've just translated from scratch into C all of these basic building blocks like loops and conditionals, Boolean expressions, variables. So sort of more of the same. But there are features in C that we've already stumbled across already, like data types, the types of variables that doesn't exist in Scratch, but that in fact does exist in other languages. In fact, a few that we'll see before long. So to summarize the types we saw last week, just recall this little list here. We had ints and floats and longs and doubles and chars. There's also bools and also string, which we've seen a few times. But today, let's actually start to formalize what these things are and actually like what your Mac and PC are doing when you manipulate bits as an int versus a char versus a string versus something else. And see if we can't put more tools into your toolkit, so to speak, so we can start quickly writing more featureful, more sophisticated programs in C. So it turns out that on most systems nowadays, though this can vary by actual computer, this is how large each of the data types typically is in C. When you store a Boolean value, a 0 or a 1, a true or a false or a true, it actually uses 1 byte. That's actually a little excessive because strictly speaking, you only need 1 bit, which is 1/8 of this size. But for simplicity, computers use a whole byte to represent a bool, true or false. A char, we saw last week, is actually only 1 byte or 8 bits. And this is why ASCII, which uses 1 byte, or technically only 7 bits early on, was confined to only 256 maximally possible characters. Notice that an int is 4 bytes, or 32 bits. A float is also 4 bytes, or 32 bits. But the things that we called long is literally twice as long, 8 bytes or 64 bits. And so is a double. A double is 64 bits of precision for floating point values. And a string for today, we're going to leave as a question mark, because we'll come back to that later today and next week as to how much space a string takes up. But suffice it to say, it's going to take up a variable amount of space, depending on whether the string is short or long. But we'll see exactly what that means before long. So here's a photograph of a typical piece of memory inside of your Mac or PC or phone. And odds are it might be just a little smaller in some devices. This is known as RAM, or random access memory. And each of these little black chips on this circuit board, the green thing, these little black chips are where zeros and ones are actually stored. Each of those stores some number of bytes, maybe megabytes, maybe even gigabytes nowadays. So let's actually focus on just one of those chips just to give us a sort of zoomed in version thereof. And let's consider the fact that even though we don't have to care exactly how this kind of thing is made, if this is like 1 gigabyte of memory for the sake of discussion, it stands to reason that if this thing is storing 1 billion bytes, 1 gigabyte, then we can number them kind of arbitrarily. Like maybe this will be byte 0, 1, 2, 3, 4, 5, 6, 7, 8. And then maybe way down here in the bottom right corner is byte number 1 billion. Right? We can just number these things, as might be our convention. So let's actually draw that graphically, not with a billion squares, but fewer than those. And let's just zoom in further and consider that, all right, at this point in the story, let's abstract away all the hardware and all the little wires and just think of memory is taking up, or rather, just think of data as taking up some number of bytes. So for instance, if you were to store a char in a computer's memory, which was 1 byte, it might be stored literally at this like top left-hand location of this black chip of memory. If you were to store something like an integer that uses 4 bytes, well, it might use 4 of those bytes. But they're going to be contiguous, back to back to back in this case. If you were to store a long or a double, you might actually need 8 bytes. So I'm just kind of filling in these squares to represent how much memory a given variable of some data type would take up, 1 or 4 or 8 in this case here. Well, from here, let's go ahead and just abstract away from all of the hardware and just really focus on memory as being a grid, or really like a canvas that we can paint any types of data onto that we want. At the end of the day, all of this data is just going to be zeros and ones, but it's up to you and I to sort of build abstractions on top of that, things like actual numbers and colors and images and movies and beyond. But we'll start lower level here first. Suppose I had a program that needs 3 integers, like a simple program whose purpose in life is to like average your 3 scores on an exam or some such thing. And suppose that your 3 scores were these, 72 and 73, not too bad, and 33, which is particularly low. Let's go ahead and write a program that actually does this kind of averaging for us. Let me go back to VS Code here. Let me open up a file called scores.c. And let me go ahead and implement this as follows. Let me include standard.io.h at the top, int main void as before. And then inside of main, let me go ahead and declare score1, which is 72. Give me another score, 73, and then a third score called score3, which is going to be 33. And now I'm just going to use printf to print out the average of those things. And I can do this in a few different ways, but I'm going to just print out %f. And I'm going to do score1 plus score2 plus score3 divided by 3, close parenthesis, semicolon. So just some relatively simple arithmetic just to compute the average of 3 scores if I'm curious like what my average grade is in the class with these 3 assessments. All right, let me go ahead now and do make scores. All right, so I've somehow made an error already, but this one is actually germane to a problem we hopefully won't encounter too frequently. What's going on here? So underlined is score1 plus score2 plus score3 divided by 3. Format specifies type double, but the argument has type int.
Format
well,
code.
what's going on here? Because the arithmetic seems to check out. Yeah.
You have to cast.
Correct. And we'll come back to this in more detail. But indeed, what's happening here is I'm adding 3 ints together, obviously, because I defined them right up here. And I'm dividing by another int, 3. But the catch is, recall that C, when it performs math, treats all of these things as integers. But integers are not floating point values. So if you actually want to get a precise average for your score without throwing away the remainder, everything after the decimal point, it turns out in this case, we're going to have to, we're going to have to convert this whole expression somehow to a float. And there's a few ways to do this, but the easiest way for now, I'm just going to go ahead and do this up here. I'm going to change the divide by 3 to divide by 3.0, because it turns out, long story short, in C, so long as one of the values participating in an arithmetic expression like this is something like a float, the rest will be treated as, promoted to, so to speak, a floating point value as well. So let me now recompile this code with make scores, enter. This time it worked OK because I'm treating a float as a float. And let me do /scores, enter. All right, my average is 59.33333, and so forth. All right, so the math presumably checks out. Floating.
OK, so we're done with another hour of lecture. And so just a summary of what has been discussed over the past hour. It finished with the programming from C from the previous hour, and then also it started with also with the topic of arrays, but have not yet discussed it in further. But along the way, several things has been discussed. The CLang or the clang. It is the actual compiler that compiles your C code. So make is just like a program on top of clang or CLang that simplifies or makes or does the everything that involves in compiling the your code. So yeah, with C lang it I would make does the linking and all of the rest to make it easier for you. But behind the scenes, it's using C lang. Okay, the sort of like the actual compiler itself. So with compiling or like uh, producing, turning your C code into an actual runnable or executable program, it is called compiling. So with compiling, there are four steps on it. So there, the first one is pre-processing. So with pre-processing, it it finds and replaces all of the includes on your source code. So if you remember with C, you have the C include uh, portions at the very top of your program. So they are getting uh, the part of the compiling process is that code within that is getting taken and then placed into your code. Okay, and then the next step is compiling. So this is the actual compilation of your code, which means that uh, from your C source code, it gets compiled into assembly language. So assembly language is uh, a step lower than the actual than C. Okay, it's much lower level than the C language. It's still a language, but much closer to uh, machine code. Okay, and then after that, after compiling, the next step is assembling. So now, after it has turned into an assembly language, the next step is turning it into the actual binary code. Okay, which means they are the ones and zeros. And then after that, the last step would be linking. Now, with linking, it is combining the different, the generated binaries, okay? Which means that if your code has several includes or depends on several libraries, generated as binaries from those code is combined into a single uh, executable code, okay? Then that now produces your uh, executable program. Okay, and then as also mentioned, debugging. Part of coding is when you debug code, which means you are trying to fix issues within your code. It could be compiler issues or it could be logic issues, okay, or logic errors. And so one way of dealing that is by using the debug 50 command built into VS Code that allows you to step through or pause different sections of your code so that you can inspect and look into the different values of your variables. So another way also that has been mentioned is the rubber duck technique. So rubber duck is a way of uh, debugging, like wherein you literally you have a rubber duck, a toy rubber ducky, then you talk to it, you say or you discuss to it the flow of your logic or the flow of your program, whether it makes sense, whether uh, the error the error that you're dealing with is correct. I mean, whether your logic is correct, and then it's related to the error that you are encountering. So yeah, eventually, when you do coding that often, there would be time that you wouldn't actually need a rubber duck or something that you could uh, talk to. You just stare at something, mostly at the ceiling. When I do programming, I just stare mostly at the ceiling, trying to think over uh, my code and the logic, and yeah, think actually fixing it in your mind. It's one way of doing it. It's quite difficult to explain unless you get to experience it. So yeah. And at the end of it also, he had talked about data types. So a quick review about the different data types supported within C. And yeah, that wraps up our number 5 of the Harvard CS50 Computer Science course. And we have learned a lot, especially uh, the compiling, the different steps of it. And yeah, so hopefully we enter into our 6th hour and we would be a quarter of the way through this CS50 course. And so don't forget to like and subscribe our video so that you can follow, you get updated with our future, new videos that would come out and new tutorials that I will be putting out soon in the future. And yeah, I hope you enjoyed this one and uh, enjoy, continue learning, and have a great day, everyone. See you soon. Bye bye.